Okay, so thanks everybody for coming. We are very happy to start the year with Peter Wittek from ICFO on this very hot topic, quantum machine learning, let's say. Of course, I mean, we are all seeing in the news and all this news about the boom of artificial intelligence, which is basically based on new developments on machine learning, deep learning, all these things. And also, in parallel, maybe more quietly, but there is also this boom of quantum information, quantum computing stuff. No? So it's kind of natural to think about how to bridge these two things. And that's basically what everybody is doing now. But some people were faster and were thinking about it years ago. And one of them is Peter Wittek, who even wrote a book about it like 3 or 4 years ago. So, thank you very much.
Okay, so I assume that you don't really have much background in machine learning and artificial intelligence. So I'm going to start with that, like explaining what these concepts are and what the hell deep learning is and why I don't like it. And then I will give you an overview of different things that people tried because there's like a lot of hype of how this connects to quantum info. But once the hype dies down, there will be a few very interesting research directions to pursue. So by the end of the talk, I hope you will see what are these directions, and I will close with some open questions. So let's take a look at like possible interaction between the quantum info and machine learning. It goes 2 ways really. One way to think about it is that, okay, so we have some quantum resource and how can we use it to enhance some learning algorithm. So the cheap way of using a quantum algorithm is that, okay, so you have Grover search and you can have a theoretical speed up, a theoretical quadratic speed up, and whenever you see a minimization, you just replace that minimization with Grover search and that's it. But this is not very interesting. So the question is like, what more can you do? What is interesting to do, rather than just the speed up in machine learning and AI? And the other thing is, and this received far less attention so far, is to use machine learning in quantum control problems and in various problems in quantum physics. So there are only just a handful of papers on this, maybe 6 or 7, but this is also very promising in situations where giving some explicit control algorithm is difficult. So it's just easier to learn it and see what we get. So I'm going to talk about both directions, and also there are things in between. So you can use some quantum resource to improve a learning algorithm, which then you use for quantum control, for instance. Okay, let's get started with just the theory of machine learning and AI. So we are looking for theories that generalize well. That's the whole concept of machine learning. That's why it is very different from statistics. In statistics, you are interested in patterns in data, but you assume that, okay, you have n data points and you want to get the best possible estimate on some parameter given these data points, say the smallest variance, and that's it. Whereas that's the starting point for machine learning. So you are again interested in patterns in data, but your n data points are where you start with, and you're interested on what else can you say after you receive more points later. And you don't assume anything about the distribution typically. Whereas in statistics, you normally have parametric methods where you assume certain underlying distributions. So what makes a good theory? Before we go to a good theory, just like the big picture of how AI, machine learning, and deep learning relate. So I would say that AI is the largest possible set of all things. It includes many things. It includes the statistical patterns that I've been saying, which is related to machine learning. We always look at some statistical ensemble and data. But it also includes formal reasoning methods, first-order logic, and this symbolic AI. So these 2 threads have been around from the very beginning of AI research, which was like 1950s. And then machine learning became very successful in the 1980s. But these days, AI is catching up. So once the deep learning hype dies down, then we will see again new and interesting approaches to artificial intelligence. So what's deep learning? Deep learning is a very small and very uninteresting subset of machine learning. It's uninteresting from a theoretical perspective. There's nothing deep in it from a theoretical sense. All you use in deep learning is gradient descent. Like that's the most complicated algorithm. So deep learning means that you have some very large artificial neural network, and that's it. You will see soon enough what kind of limitations they have. So the limitations go back to the question, what makes a good theory? And this has occupied human minds for thousands of years. And we know that the theories that we like the most do not have many assumptions, but they apply in many, many, many different situations. So this idea was first formalized in writing by Aristotle, like 2,400 years ago. And then came the Dark Ages, and then we associate a name with this principle. We use it, Occam's razor. William Occam was a monk in the 1300s, and he said that among a bunch of hypotheses, we want to choose the one with the fewest possible assumptions, because he thought that generalizes better. That has the most possible number of applications. Plus, if you have a theory that works in certain experiments well with a minimal number of assumptions, it's always easy to add completely arbitrary assumptions. So this is one more reason to choose the simplest one. Actually, if you go through the complete works of William of Occam, which is like many, many thousands of pages, he never wrote down this principle, but somehow we associate the principle with his name. So machine learning formalized this idea of Occam's razor in a statistical setting. But let's talk about the major schools before actually going to this formalization. So the two competing methods were around from the very beginning, from the 1950s. One is connectionism. So this was the idea that, okay, let's take the human brain as a model where you have neurons connecting to each other, which register certain correlations and reinforce certain correlations, and let's use that for learning and see how it generalizes. And this goes into deep learning in the end, what we use today, very large neural network. And what you do here is very, very similar to actual statistical inference. You use some empirical risk minimization on certain parameters in the model. And the other big school is the symbolic AI, first order logic, and other forms of formal reasoning. And there are a few others that came along on the way. I'm a big fan of structural risk minimization, which was formalized over the course of 30 years. And it finally achieved its final status in 1995. And this is the theory that really summarizes and gives you very strong guarantees on Occam's razor and why it works. And support vector machines were based on structural risk minimization, and they were the king of the hill for 10 years, between 1995 and 2005, until deep learning took over for very specific reasons. And then you have something in between these statistical approaches and formal approaches, which is probabilistic graphical models, which are like Bayesian networks and Markov random fields, which encode the sparsity structure of a certain joint probability theory. And you have some idea of causation, but it's not very strict, not as strict as in inference, as in formal inference. But you can also address correlations in the data that you observe. But if you ask the next machine learning researcher, he will give you 4 or 5 completely different schools of thought. It's just my categorization. So let's look at the relationship of machine learning to statistics, AI, and to itself in a bit more detail. So in statistics, most statistics is inferential statistics. Maybe 90–95% of the whole field of statistics is inferential statistics, and out of that, most of it is some parametric inference, where you assume certain parameters about the distribution or whatever observable you want to estimate. And you use loads of large numbers and concentration theorems to derive certain limits based on your observations. So think about quantum metrology, where you use concentration theorems and an IID assumption, and you know that that your figure of merit, say variance, scales as 1/n. But if you use quantum entanglement and you get rid of the IID assumption, you can scale much better. You can scale in your figure of merit as 1/n squared. There's a quadratic boost in a specific type of complexity. Here, n is the number of sample points, so it's a sample complexity. And sample complexity remains essential to machine learning, but it adds new forms of complexity into your thinking. Then let's look at AI. So let's look at a very simple knowledge base of first-order logic. Imagine that you are some guy Y who wrote a paper, and you get a referee X. And if this referee X reviews your paper, then we say that he's competent. You know, it's a long shot. So it's usually, well, sometimes it's not true that you get a competent referee. But this is what we can encode, that for all x, y, this thing holds. And the reason it is called first-order logic is because you have these quantifiers over your variables over objects. So for all x, y, that's why it's first order. Second order would allow quantization, for instance, on the referee. It could apply arbitrary predicates on the variables. And let's have a second proposition, that referees of physicists are always physicists. This is more plausible, although I'm a half-baked mathematician, half-baked computer scientist, and sometimes I review physics papers, so this is also not entirely true. And now the question is entailment. So now you're given a specific formula, so now we fill in the slots. So Alice wrote a paper, and Bob referees it. But we also know that Bob is completely incompetent. So is it possible to derive this formula from your knowledge base of two formulas? And the answer is no. But to arrive at this answer, that's a very, very hard problem. It's computationally very complex. In fact, it's NP hard. So this is where computational complexity enters the picture. So first of all, inference is expensive. And on the other hand, if you really want to have accurate description of reality, you have to add more and more clauses. That, okay, so this guy referees your paper, and he has degrees from this and that university, and you add more clauses, then he is competent. So you have this combinatorial explosion of formulas. Your formulas will be very, very, very large if you want them to correspond to reality. So inference is expensive, it's computationally expensive, plus your models just keep expanding in size. Plus, if you have a single contradiction in your knowledge base, then you can trivially derive any formula from it. So you have to be very careful. So there was this boom of AI research in the 80s, where people were building these very large knowledge bases for certain domains, like engineering domains and medical domains, but they just couldn't codify everything they wanted. And at the end of the day, they contained contradictions, and they were completely useless. So you don't use this kind of rigid symbolic AI today so much. So there's one complexity that is missing from the picture. So we talked about sample complexity, which relates to data. Now you have this computational complexity, which refers to how expensive it is to make calculations with the knowledge that you extract. And you want to characterize this model complexity. You know, now in this first-order logic, your knowledge bases grow very fast. You have the combinatorial explosion. So machine learning adds this to the picture, a quantification of what model complexity is. So I want to give you one particular type of model complexity. There are several measures, but I think this is the easiest to comprehend. So if you look at this formula on the top, I can't use a laser pointer because it will not show well in the video. So let's look at this formula on the top. So imagine that you have a fixed set of data points that you are given. Okay, so you are given n data points which live in some high-dimensional real space, and each has a fixed label associated with it. I say yi, and you want to learn something about the connection between the labels and the data points. And the question is that, okay, now you have a parametric family of functions, and you want to find a function in this family which fits these data points the best, that assigns the labels in the best possible way. And what model complexity gives you is a description of your function family, of your parametric function family. It tells you its ability to pick up completely random noise. So that's what this measure characterizes. So now we have a decision function H, well, that's a function from your function family, that can assign labels to your data points. And you have a random variable, this sigma I, which is called the Rademacher variable, which can take plus and minus values, plus 1, -1. Your labels can be plus and minus 1, right? So what it measures is it's the correlation, the best possible correlation of what your function family can learn and completely arbitrary labeling, right? So if it can pick up perfectly arbitrary labeling, then this will be maximal. Then it will be n or something like that. And if it's a very stupid function, then it has no capacity to learn anything, then its complexity will be very, very, very low. Like think of a hyperplane, which, and think of a hyperplane and think that your points live in some curved manifold. Then it will not be able to pick up all the labels correctly. So this is the empirical Rademacher complexity. It's empirical because it looks at fixed data points that you are given. And if we also average over all possible n data points that you get the actual Rademacher complexity. So this is one measure of model complexity. And basically what you get in machine learning is a certain guarantee. And what I highlighted here is the guarantee that you get. So on the right-hand side, the first figure is your training error, like the best possible error that you can get if you pick the best function from your family on a fixed data set. So that's data dependent of what that error is. And the second one does not depend on the actual data points. It depends on n, on the number of data points. So this is the sample complexity aspect of it. So if you keep increasing the number of your data points, then of course this bound will be tighter. And you also have the model complexity. And this capital F function is monotonic in the model complexity. So it monotonically increases as the model complexity increases. So and on the left-hand side, you have the generalization error, like your error rate on your entire distribution without assuming anything about what that distribution is. So you are given a completely random sample, you get some error rate on it, and you know the complexity of your function family. And this allows you to give a guarantee of how well you will perform on instances that you have not seen before. So if your model complexity is low, this guarantee will be very tight, but your training error will be high. On the other hand, if your if your family is too complex, like you can have perfect error rate, but your complexity will be high, and therefore your guarantee will be extremely poor. So this principle is the statistical formulation of Occam's razor. We prefer sparse models. We prefer models which are not too complex, which are just complex enough to capture the phenomena that we are studying. So this is the essence of machine learning. And this also tells you why deep learning sort of works, but not quite. Because every single deep learning model has like millions of free parameters. They're extremely complex. They have a very high model complexity. So this guarantee is very poor. You don't get any guarantee for deep learning networks how well they generalize. So there are two reasons why deep learning networks work. One is that you have many labeled instances. So this became available really like 10, 12 years ago with like massive collections of images that people tagged, for instance. And then the tags act as labels, and plus you have the image as the input data. So your sample complexity for these things is just very, very high. Your n is very, very high, and because of that, this guarantee sort of works, although you have very complex models. And the other reason is that they work is because now we have, so deep learning networks are very easy to parallelize. So they run very well on graphics processing units, and if you put them on a cluster, like a large cluster of graphics processing units, then they can be trained in a reasonable amount of time. So computational advances and advances in available tagged data enabled deep learning. But still, like this guarantee is not really there. And there's one more assumption here. So we don't assume anything about the distribution, but we assume that your sampling is IID, which of course goes away when you start using phantom resources. So it's easy to talk about like the high theory of machine learning, but I also think it's better if you get a grasp on what's an easy and what's a difficult problem in machine learning. So when you have labels, that is, you have supervised learning, that's the easiest. That's where like deep learning like aces everything, because there's so much data and there's so many labels. Semi-supervised learning is when you have some labels and you also have like a large pool of data which are unlabeled, and then you sort of propagate labels and try to learn what's there. Then you have unsupervised learning, which is like finding trends or grouping similar instances together, where you don't really know what you are looking for. You just deploy an algorithm and you hope that something will emerge, and that may or may not happen. And then you have generative models, which are, for instance, you tell an algorithm that, okay, read these books and like write me an essay in a similar style. And then you have reinforcement learning, which is the hardest of them all. And this is halfway between machine learning and control, is when you can act on the environment. So you receive inputs from the environment and you act on it, and there is some reward function telling you how good you are. So this is what is being started to being used in quantum control. And when we look at it from the perspective of data, we love structured data. Structured data is things that you can put in a spreadsheet. So rows, columns, numbers, very, very simple. Semi-structured data is it's like an HTML file. So there are some tags, but there's also some unstructured stuff like text. And unstructured is like text, images which don't really have any kind of structure to them. And this is the vast majority of data out there, like 90% of the data out there. So think about a very easy problem today is image classification. So you're given these 256 pixel by 256 pixel images, and then you're given labels for them that this is a boat, and this is a don't know what, and this is what deep learning can do very well. So I think this is the CFAR10 data set. Like on this, they have a 99% accuracy of labeling an image correctly. This is one task where deep learning algorithms overtook humans. So for instance, these self-driving cars by Google recognize traffic signs with double the accuracy than humans. So this task can be solved. And then here's another one. It's a game I played. So I was curious what we can use with a deep learning algorithm if it does not know the language it is trained on. So I fed abstracts from QuantPH on Archive into a deep learning algorithm, and I gave it a seed. I gave it a seed phrase, and I told him that finish this abstract if the abstract starts with this seed. And the seed was, the foundations of quantum physics are, and this is what it gave me. It's completely nonsense. But think about it, that it trained only on a few thousand abstracts. It took about 1 hour to train it. It did not know English. It did not know what space was. It did not know what punctuation was. Okay, it doesn't show punctuation, unfortunately. Oh, there's a full stop there. So it picked up everything by itself. And it is sort of a meaningful English sentence. Like if you give it more data, it would be able to figure out the rules of English. So I thought it was a curious experiment. That's my second last slide on classical machine learning. And I thought it would be interesting to tell you, like, if you want to get started with machine learning, then where you should look for resources. I can't recommend you what everybody recommends you, which is Andrew Ng's course on Coursera, because that course assumes that you don't know linear algebra or calculus, which is a long shot, so you would be bored out of your brain. I highly recommend you to learn it by doing. The lingua franca is Python, luckily, because Python was one of the first languages which was designed for humans. Then there is this really cool book by Sebastian Raschka, Python Machine Learning, with plenty of examples. It also assumes that you have like just very, very little knowledge of linear algebra, but then again, like the examples are complex enough to keep you entertained. It is worth learning one deep learning framework. When I implemented this abstract generator, I used Keras. In 5 lines of Python code, you get an enormous deep learning network, and you can do magical stuff with it. And then when I was doing this experiment on the abstracts, I made the dataset available on Kaggle. So Kaggle is a website for people who are interested in machine learning. There are many machine learning professionals there. So without installing anything on your computer, you can just log into Kaggle, run Python experiments on their cloud infrastructure. There are many data sets, including this archive.ph, and fool around with other people's code. You can change that, right, or start from scratch and do your own. So I highly recommend fooling around with that. OK, so that's it about classical machine learning. So now we can move on to quantum enhanced learning, which is a lot more interesting. So there are a couple of synergies here. This is like the grand picture, which also includes classical machine learning in quantum physics problems. So out of all this big thing, I think the very, very first example of quantum machine learning was, I don't even see, oh, here. So it was quantum neural networks. It was a paper was published in 1994 by Maciek Levenstein, which was completely unnoticed for 20 years. Actually, it's still completely unnoticed. He was interested in a curious question. He was interested that, OK, so a perceptron, a perceptron has a certain capacity to store patterns. And he asked the question that, OK, what if it's a quantum perceptron? Like, then what's its storage capacity? So he asked the right question, because since then, most people were concerned with the speed up, which is not so important. The question is the capacity, like how much we can learn with something. And he asked the right question as the first guy here. And then the second one was maybe 2009, 2010 here. So Giulio Chiribella asked the question that, OK, so what if we use certain ideas from learning theory and use it for state tomography or process tomography? And he had two very interesting papers on that. And then the boom started in 2013 when we had quantum support vector machines, which are actually not support vector machines in the way machine learning people like it. Then there came quantum principal component analysis and all this other stuff, and quantum annealing by D-Wave mainly. So let's look at this exponential speed up claim from 2013, like Seth Lloyd and his followers. All of these algorithms that claim an exponential speed up in machine learning assume, first of all, that you have quantum data and some quantum RAM or some very efficient state preparation protocol to start with. And you need some n copies of your data, or whatever number of copies of data to make the protocol work. And each and every of these algorithms relies on the HHL algorithm from, I think that's 2008 or so. So you assume that you can do matrix inversion very, very fast. So out of this like set of algorithms, I think and principal component analysis is good, and singular value decomposition is also fun. And then they had this topological data analysis, which they claim to be big in machine learning. It's not. It's a tiny niche in machine learning, but that's also a good application of the HHL. But quantum support machines, which receive the most attention, are just bad. It's because, as I mentioned before, they were derived from, support vector machines were derived from this idea of structure risk minimization. So you wanted to have sparse models which adhere to Occam's razor. And they changed the formulation. They changed to least squares support vector machines so that they can use the HHL algorithm. But they lose something. The model will always be maximally complex. So it's completely pointless to use a maximally complex support vector machines. It goes against the principle. So from a learning perspective, it's irrelevant. Anyway, so most of the excitement was because of these applications of HHL algorithm, and I think the low-hanging fruits are gone. So hopefully now we can focus on something more serious. And if you factor in state preparation protocols and state tomography in the end, then you cannot possibly get an exponential speed up. So it's more like a polynomial. Then there are a bunch of other models which require universal quantum computers. There were a handful of not terribly exciting papers on using Grover search as a building block. Again, like wherever you see a minimization, you can just plug in Grover search. But you need a discrete search. So for that, you have a few options. One, you discretize your search space. We normally optimize over some continuous space, and then you lose something by discretization, and then you have to think about how you do that. And the other is quantum associative memories. So there are certain neural networks which do nothing but like storing patterns. And you can do that via quadratically faster, almost quadratically faster with Grover search. That's a little bit more interesting. And then you have quantum deep learning. There was a paper on it 2 years ago, and it's finally getting published somewhere, I think in Quantum Information Computing, which was a very nice idea of, okay, so you take a specific kind of deep learning machine, which is a stacked Boltzmann machine. It corresponds to a Gibbs distribution, so you could just use a state preparation protocol, just prepare a thermal state and sample it, and voila, you trained your learning model. So that's an idea. But again, for this like prepare and measure protocol, for the preparation, you need a universal quantum computer. And this was Giulio Chiribella's original idea in 2010 for using certain ideas of learning theory. So he said that, okay, you have a black box that implements some unitary, some fixed unitary, and you can use it n times, and after that, your black box is taken away, and your task is to replicate what the black box did like k times. And this is a very, very specific type of problem in machine learning. This is called transductive learning. And he asked the question, okay, so what should we do? Should we do a kind of process tomography to understand what this black box does, or should we keep it in some quantum memory, what it does, and then apply that? And curiously, it's the measure and prepare protocol that's better. So you have to do some kind of tomography, and that's optimal, which is very counterintuitive actually. And then we have seen many experiments with quantum annealing and Gibbs sampling. So this was driven by D-Wave. So D-Wave has this quantum annealer, which has 1,000 qubits, but they are very, very specific in connectivity. And some of the qubits are dead to make it more complicated. So it's hard to use. And they do annealing in a like a non-standard way, so they anneal too fast, so they cannot guarantee that they stay in the ground state when they change the Hamiltonian, the parameterized Hamiltonian. So what you can't really use it to solve non-convex problems in a way you want them. So you don't find the global optimum, although that would be like terrific for learning theory. In learning theory, we usually come up with an objective function that's non-convex. And then we come up with some convex relaxation so we can solve it efficiently on classical computers. But by going from non-convex to convex, you lose something in generalization performance. You usually end up with more complex models. So if you can solve the non-convex problem directly, that's hugely valuable. Speed doesn't matter, it's just a generalization performance that will be better. But you can't do it with the D-Wave chip. But what people noticed is that if you keep annealing, and you get a bunch of excited states in the end, then these excited states follow a Gibbs distribution, approximately. So now if you can map your problem to the chip, then the specific connectivity, you keep annealing, then you can actually generate a Gibbs distribution and you use that for sampling. So it's like an other way of thinking of like, okay, thermal state preparation and measure protocols. So they use it for training Boltzmann machines. But you can't scale it up very well because the newest chip has 2,000 working qubits in this very specific topology. Then we have tensor networks and deep learning. This is really fun. I'm very excited about this. So nobody really understands why deep learning works. There's no mathematical framework for it. We know that we have like these stacks of layers of neurons, one after the other. But we don't know how representation evolves between the different layers. So we know that, okay, in the input, we have the raw image. And as you go higher and higher, you extract certain features. Say you extract the boundaries of objects, and you go further and further. But there's no theory for it. And then you look at tensor networks, and you look at Mera, for instance, which solves one-dimensional systems in a hierarchical way. And it allows you to focus on the part of the Hilbert space where the interesting things happen. And you can make some connections between the representation layers in Mera and these layers in deep learning. So research started on it basically last year, and there are maybe 4 or 5 interesting papers on it. And it's a very, very special area of research, because a paper on this managed to make it to NIPS, which is the biggest machine learning conference in the world. And they usually just reject anything that has quantum in it, and this paper made it. So it's a huge success. Unfortunately, I was not a co-author. Then you can ask more fundamental questions. Okay, abstract away all possible algorithms and hardware and anything, and just like think about it. Okay, so there's a certain basic components of learning, and this is what you can derive with statistical methods, assuming classical distributions, and what happens if you move further. So last May we had a paper on this, which we got rejected from NIPS, which proved that there is some asymptotic equivalence when you think of inductive learning. So it's kind of supervised learning where you want to when you want to induce a function. So there's no advantage there, but to prove this, we actually had to prove a quantum definite theorem for channels as a side result. So I think that's the real value of the paper. Then Vedran Dunchko and Hans Briegel said that, okay, let's look at reinforcement learning. Like we are in some quantum environment, you have a quantum agent, and the environment is also quantum. How do we verify that this agent learned anything? And they analyze these questions, and they realize that you can get an exponential speed up until you don't make any measurements to verify what the agent does. But the moment you start verifying the agent slows down to at most Grover search speed, so you can get at most quadratic speed up. So they published that paper in PR last October. But there are lots of things missing. We don't have complexity measures for the quantum case. We don't get these nice guarantees on generalization performance as we do in the classical setting. So these are all open questions, and these are difficult questions. So let's look at a few implementations. These are mainly proofs of principle, and most of them are neural networks. And the problem with quantum neural networks that apart from Maciek Lavenstein and maybe Nathan Weave, that most people who do research on or ever did research on quantum neural networks are complete crackpots. So I'm very tired of reading papers about quantum neural networks, but most implementations are for neural networks. So you can, in principle, you can use quantum dots to implement them, but nobody actually did. That's a proposal so far. And there are a few photonic implementations, and there's also some adiabatic work, and with D-Wave, and also with a nuclear magnetic resonance system. But all these are always just a few qubits, so not terribly interesting. And there are fewer implementations of things that are not neural networks. 2 years ago, they implemented Seth Lloyd's proposal for support vector machines, and also for k-means clustering. One is 4 qubits, and the other is 8. And that's about it. So you can't really scale up that up further. They also investigated whether Seth Lloyd's quantum realm proposal is scalable, and it's not. And now there are a few ideas to do machine learning with continuous variable systems, which is again like very, very good for photonic implementations. So my conjecture is that we will see more and more photonic implementations of various learning protocols, both continuous and discrete variable systems. Okay, so let's look at the other perspective. So now we want to apply machine learning in quantum info. So there are very, very few papers on this. So this is just a rough timeline. So Barry Sanders was the first to do it. So he came up with this idea in 2010 that, hey, why don't we use reinforcement learning and some heuristic search to do adaptive phase estimation? And then he had a few follow-up papers on that. Then Hans Briegel in Innsbruck was interested in okay, so he's very interested in measurement-based quantum computing, and he asked the question that, okay, what if we relinquish control to some agent? Then what this agent should do to control the measurement-based quantum computer? And he had some very, very interesting ideas on that, and now he has this paper that I mentioned here in 2014 managed to adapt to some changing magnetic field to adapt the measurements. Then in 2015, there was a cool paper of using Bose-Einstein condensates using reinforcement learning. Then they quantized the agents, again, Hans Briegel and Vedran Duchko in 2015. Plus, you also have a a few other problems where the question is not so much control, but like how you map to a universal set of quantum gates to a particular implementation, say with an ancilla, without thinking, like just using learning. So I want to go through some of these very quickly. So this is the additive quantum phase estimation. You have this interferometer, you have this large entangled state, which is optimal in a sense for phase estimation. And you have an unknown phase, and you have another phase shifter which you can control. And by adapting this controllable phase shifter, after consuming all your particles, this adaptable phase shifter will tell you exactly or approximately the unknown one. And how you do it, that's an open question. And it turns out that you can use heuristic search and reinforcement learning to do it extremely efficiently. I'm involved in this research. At the moment, we are up to 100 particles, and we try to scale it up even further. The idea is to go up to 1,000 particles, but actually we are very far from that. The problem with this is that it's very expensive to do. So it has n to the 7th complexity because of the figure of merit that we are estimating, and also because of the heuristic search. Okay, I still have time, a little bit of time, so I don't have to rush so much. Yeah, these are just very quick results. Maybe the curve that you have to look at here is that this dotted purple line, which is the Heisenberg limit. Like we are super far from it. And the SQL is this light blue. And the question was not so much to get close to the Heisenberg limit, because you can't do it anyway if you have noise in the system and all that. You lose that scaling with quantum phase estimation. But the question was like how far you can get from the SQL. And if you keep adding noise and so on and so forth, it turns out that our algorithm, which is denoted by DE for differential evolution, can deal with various kinds of noise. And as the system size increases, you have more and more particles, the scaling gets better, and you get further away from the SQL. And so this is this other type of learning where you try to map quantum gates to some system which is not designed for quantum gates. And you can do this with supervised learning. So this is the work by Nicola Pancotti and Leonardo Banchi. Nicola is in NPQ, and Leonardo is in UCL. So they were thinking of that, okay, so we know this particular type of computing model very well, some ancilla system, and you map gates there. I think these are spins, and you can do computations on it just by waiting. And they were thinking that, okay, but like mapping gates to this by hand is hard work. So why don't we use just something like a neural network? And they did. So they have a training algorithm which is almost identical to how you train deep learning models. And they get some pretty exciting results. So that's one way of doing it. The difference here is that instead of having a fixed sample with labels, as in supervised learning, you are back to the model that Giulio Chiribella had for process tomography. So you have a black box that you can call, and that's what gives you the figure of merit for the supervised learning algorithm. So the last topic I want to talk about is moving towards AI. And why would you move towards quantum-enhanced AI? Like, why is quantum machine learning not enough? In machine learning, most of your computational time and everything goes into this sample that you are given. So once you train your algorithm on that, let that be supervised or an unsupervised problem, it doesn't matter. It's very cheap to use the model. And you also get your generalization performance, so you know how approximately how well you will do on these unseen data points if you keep applying your model. But in AI, inference remains expensive. So whenever you're given a new statement, for instance, this was the example with Alice and Bob, that one reviews the paper of the other, but this guy is not competent. Like deriving this inference is a hard problem. It remains hard, even though you already have your knowledge base compiled. So I think quantum-enhanced AI is interesting because you will continuously need quantum resources. It's not like that you train your model and you throw away your quantum resources. It's something for which you have to maintain your quantum system and you have to have access to it. So we started working with it with my colleague Christian Govalin. We were looking at probabilistic graphical models. So these are the models which are halfway between the statistical machine learning methods and the AI, which managed to capture certain sparsity structures in joint probabilities. So think of a Bayesian network where you have things like, okay, the grass is wet and there are two possible causes. One, it rained, and then that somebody switched on the sprinkler. And then like, what's the probability of going from the sprinkler or the rain to the observation that the grass is wet? So there is some causation here, but it's like soft. Like there's a direction of inference or impact, but it's not like a strict first order calculus. The real thing here is that you have a bunch of things that you can observe. So there can be, you know, the color of the car standing next to the grass, which is irrelevant to the wetness of the grass. So obviously you have to ignore that correlation, but you know there's a strong correlation between rain and the grass. So a Bayesian network or a Markov random fields captures this sparsity structure in your joint probabilities. So Markov networks are models which don't care about the direction of the inference. So they only want to capture the correlation structure, and that's it. And it turns out that if you have a very mild assumptions of how you construct your Markov networks, they correspond one-to-one to Gibbs distributions or Boltzmann distributions. In fact, this machine learning model, Boltzmann machines, which people keep training on D-Wave hardware, are just a specific type of Markov network. And D-Wave uses Boltzmann machines because of the limited connectivity of the hardware. They can't train a generic Markov network on it because the way the qubits are connected, most qubits are connected to 6 other qubits in a very specific way. And if you have like long-range interactions in these Markov random fields, like correlations between very remote nodes in the network, then you can't map it efficiently to this chip. Whereas in Boltzmann machines, you have a very restricted connectivity, and you can map it to the hardware efficiently. So we are thinking, and okay, so Markov networks are too general, although they correspond to Boltzmann distributions and Gibbs distributions. So what if we can guarantee certain properties of the graph of the Markov network? And this is where these really cool models. Oh yeah, one more thing about this. So inference remains expensive in these graphical models too. So it's Sharpie. It's even more than NP hard. So it's worth thinking about this problem. So there are these very interesting learning models, which are called Markov logic networks, which marry first-order logic with Markov networks. And in the process, we get something that we were looking for. So what these Markov logic networks do is they use first-order logic as a template to generate Markov networks. And this Markov network will have very, very specific properties. For instance, if we have a locality structure. And if it has a certain locality structure, then it's easier to map it to the hardware, to the annealing hardware. And then we looked at the properties of the graphs that we generate, and we realized that, okay, but you still can have like nodes with a very high degree, and that's just a no-go for the D-Wave chip. So we turned to like generic models. We looked at universal quantum computers, and we realized that we can also do state preparation protocol, and we used the state-of-the-art protocol from last March, and we managed to get an exponential speed up over on inference on Markov logic networks, which are just infinitely more exciting than these boring Boltzmann machines. So there is something here, but the good news is that you have this exponential speed up, and the bad news is that it's still exponential in the number of nodes, the number of observables that you can have. Plus you unfortunately still need a universal quantum computer, so you can't just use a D-Wave chip. And there are no-go results here, but I'm out of time, so I leave it there. I want to finish with a few open questions. So in the long term, we will very soon reach limits of deep learning. They don't generalize. So for instance, you train them on images of cats and dogs, and you give it a picture of a boat, then it will not tell you it's a boat because it has never seen a boat before. And we need learning algorithms that can do this generalization. Plus, they need many samples. So they can't do what humans do. Humans are very, very good at one-shot learning, that they see something for the first time and then they recognize it forever. You can't do this with deep learning. But its success was enabled by data and by computational power. So quantum resources have a role to play here, especially when it comes to capturing coincidences, certain correlations, and in computational complexity. And we can also look at machine learning and AI in general as something that will enable us much better quantum control that we have, and with less thinking. So we build AI and machine learning because we want to save ourselves from thinking. So if we can just deploy a reinforcement learning algorithm to control a quantum computer, then why wouldn't we do that? But that's a long way to go. And there are other questions which we can address, shorter term, mid-term. Quantum annealing is there. It's a real technology. It scales very well. D-Wave is one example, but other companies are also building squid-based quantum annealers. So you'll see more and more of this technology. It becomes cheaper and cheaper. The question is what we can use it for. Can we come up with more experimental relevant protocols? So I think this is where photonic implementations are very, very relevant, especially continuous variable systems, because we can map them to learning blocks in learning theory. So that's a fun way to go, and most of them are room temperature, so you don't need this like huge freezer as you need for squid-based annealers. I mentioned this favorite topic of mine, risk minimization, and quantum resources, completely open, but it's also very hard. Then the reinforcement learning methods used in quantum control so far are from the early 1990s. So we are working on making them a bit more contemporary. Then you can use this like sandwich method, right? So you get an idea from learning theory, you use quantum resources to implement it, but you implement it to, say, control a quantum system. That's very, very unexplored. There are just 3-4 papers on that. And then there is this other cool thing of the connection between tensor networks and deep learning. And that's my last slide. So thank you very much.